You've invested in software architecture to ensure your system is extensible, to provide for future growth and capability that's affordable and timely. Properties like extensibility are hard or impossible to test. You verify these in your architecture, not your implementation. What do you do when developers change the code and diverge from those guidelines? It's not until months or years later, when you're building the next release, that you discover the discrepancy. Integration is delayed, and you need to rip the system apart and make it work again. I'm Robert Nord. In this session, my colleague Lena Pons and I will walk you through a second-year research project. We're developing a tool that automatically checks that each code commit conforms to its design. The prototype shows viability. We're working to extend the prototype with machine learning techniques to detect architecture elements more broadly. You can help by contributing your conformance cases to advance this research. Good architecture practice is vital for the success of our software systems. The software architecture community has grown a body of knowledge in the form of architecture styles that guides the design of a system to meet its business and mission goals. But our investment in architecture doesn't pay off when the implementation doesn't match the design. Nonconformance puts the system at risk in realizing its desired qualities. MOSA and directives like the Defense Innovation Board's commandment for iterative capability delivery provide a technical and business strategy for developing affordable and adaptable systems. FACE is a standard that provides a reference architecture to achieve some of MOSA's goals. About 40% of the FACE conformance verification items are checked by inspecting the design. Furthermore, FACE is a component-level standard and not a system standard. FACE compliant systems may still encounter integration problems. Can we do better? Can we automate more of these manual checks of inspecting code conformance to design? Can we provide more architecture checks that include the way components communicate and interact at the system level? Our vision to address these challenges is to create a tool and integrate it into a continuous integration workflow to report nonconformances in hours instead of the months or years that it takes to discover these problems today. Continuous integration offers visibility into the state and associated quality of the software system. Adding an automated checker makes use of the investment in architecture and impacts two kinds of stakeholders. Developers use the tool to detect nonconformances during continuous integration testing. Automation enables early detection and remediation. System acquirers can write contracts requiring developers to use the tool and report results, providing visibility that they don't have today. We're bounding our focus to MOSA properties. These are critical as the government moves to more iterative capability delivery. That said, the work applies to many properties. A core research challenge is extracting the as-implemented design from code. This involves the following activities. Source code seen at the left is input. We analyze the code to mechanically extract as much semantic knowledge of code structure and behavior as possible, unambiguously and automatically. Once we identify the design constructs in the code, we can traverse the code graph and abstract relations among the constructs to build design fragments. These constitute the as-implemented design seen at the right as the output. We're using a data transformation pipeline here as an example of a design fragment inspired by the FACE technical standard that follows the MOSA approach. It consists of design constructs such as filters that read input, transform data, and write output, and pipes that connect filters and provide buffering and synchronization. Bridging the abstraction gap between code structure and design is a hard problem and represents one of our contributions to the state of the art. This capability to extract design from code is part of a prototype tool that automatically checks that the implementation reflects the intended design. Design fragments represented as graphs enable automatic detection of nonconformance. These graphs are checked for agreement with the intended design to locate inconsistencies. We've selected conformance to architecture communication styles and the move to continuous integration as our starting point to grapple with these complex challenges in meeting MOSA objectives. We're applying our skills in code analysis, software architecture, and machine learning to bridge the abstraction gap. Moving from a component to a system view puts the emphasis on the interactions among components. The architecture approaches that we've seen from a decade of architecture evaluations conducted by the SCI reveal a rich collection of communication styles and underlying mechanisms supported by frameworks, libraries, and software platforms. A recent literature review shows that although technology may change over time, many communication styles are enduring as canonical design knowledge. Thus, we've selected communication styles as the types of design constructs that we're targeting. The initial style that we've selected is publish-subscribe. It's a style that limits coupling. Subscribers are coupled to publishers only through the published message, which is transported over the publish-subscribe infrastructure. Messaging is a form of asynchronous service-to-service communication used in event-driven, serverless, and microservices architectures. Any message published to a topic is received by all the subscribers to the topic. Next, we're expanding our focus to families of communication styles that share attributes that we can use to distinguish constructs within a style family. How do we find the block of code that's a publisher or a subscriber? That code may be in a repository, such as the one we see here, containing hundreds of files and thousands of lines. This is a portion of the code for Hotspot that we use to demonstrate the end-to-end capability of the conformance checker prototype. It's an open source project representative of communication styles that we're targeting. It provides a GUI for conducting performance analysis. There's about 8,000 lines of C++ application code. It uses the Qt framework to provide the publish-subscribe capability. A fragment of the source code block that we're looking for is seen here at the top. The design fragment consisting of a publisher and subscriber corresponding to the code is seen at the bottom. In between is a graph representation of the code constructed from multiple sources of information. The prototype uses static analysis to build a code dependency graph and compiler technology to annotate the graph with abstract syntax tree properties. There's the capability to enrich the code graph with information of structure and behavior through additional analysis based on the needs of detecting design fragments. Given such a code graph, how would an automated technique recognize indicators of important design properties exhibited by publishers and subscribers? Would it use rules or classifiers? What data would be needed? And how generalizable would it get? We created a rules-based predictor to enable our prototype to detect design constructs. Rules are a reasonable approach for some abstractions in commonly used frameworks. Here we see a rule for detecting a publisher by matching the structure and semantics in the code graph. This was created by examining the Qt framework, providing that publish-subscribe capability, and understanding how it's realized in the application and framework code. The prototype shows viability in using the rules-based predictor to extract design from code for a single architecture style, in this case publish-subscribe, and a single framework supporting that style, which is Qt. We've applied the prototype to other open source projects in addition to Hotspot to demonstrate local extensibility to code bases built on the Qt framework. We're also applying what we learn from open source projects to a larger case study to see how the techniques scale from thousands to millions of lines of code and generalize from the use of the Qt framework to frameworks based on the data distribution service standard from the object management group. Work on rules-based predictors is also work towards labeling data needed to try other classification approaches. We're extending the prototype to support more conformance checks. This involves moving from a single style to families of communication styles and the framework supporting them. As we develop more precise definitions for communication styles, we'll identify how different styles may be better characterized using machine learning-based predictors. Lena Pons will discuss this more general solution next.
So I'm going to talk about the design code abstraction gap and some steps towards a general solution. While we were building the prototype, we observed that characterizing architecture-level styles is very challenging. This is because the information that's required to characterize those different styles exists multiple places across the software system. In object-oriented systems, we build software with application code that's built on top of framework code, which in turn is built on top of the standard libraries for the programming language, in this case C++, which in turn is built on top of the operating system. When we think about how to generalize the work that we've already done, for example, in the prototype, we used clues from frameworks to label publishers and subscribers from multiple projects that were built on top of common frameworks. But when we think about coming up with a more general solution, we need a way to address the tremendous variability that lives in the application space. So thousands of applications are built on top of hundreds of frameworks, dozens of languages, and a handful of operating systems. When we think about how we can characterize these styles, we observe that there are a smaller number of more enduring indicators down in the programming language and operating system levels that we can use in a similar way that we use clues from the frameworks to characterize publishers and subscribers. Another challenge to this work is that many of the software styles that we're looking to characterize can look very similar, particularly in the interaction graph-based model that we've been using. So for example, a trivial peer-to-peer network and a trivial client-server network are indistinguishable at that interaction graph level. So we looked at what would be ways that we could extend out the feature space such that we could differentiate these styles across multiple different styles in the communication family. And we identified 4 key properties that were sufficient to differentiate many of these frequently occurring styles. And so if you look in the table, those highlighted cells show us that in one property, we're able to differentiate these 2 very similar styles. In order to make use of the clues extracted from multiple layers, we need some way to tie everything back to that application layer. And so we observe that in the application code, there is a call down to a method that's implemented in these common frameworks. The frameworks in turn call the programming language methods, and the programming language is called down to the operating system. In the reverse, we're able to basically tie these indicators from the lower levels back up to that application layer, which is extremely important when we go to build the predictors based on these clues extracted from multiple layers. So now we need to find not just the methods, but the properties that are related to those formalized definitions of the styles. So we identify that there are methods that are indicative of certain properties that populate through these multiple different layers within the software stack and allow us to label those, allow us to map those properties back to those method calls. Important in integrating this work into the existing conformance checker is our ability to accumulate all of these indicators that we've extracted from the different layers in the software stack back to a single representation. So we built a very powerful data representation in the code graph that Rod described earlier. Now we need a way in order to include the properties that are indicative of the styles that we're trying to detect into that common representation. So The work that we're doing right now to extract those indicators of properties will be integrated into that single code graph, which will allow us to then detect multiple styles from a single data representation. And extending even further, we see that pulling all of these things together allows us to really bridge that design code abstraction gap. So we will develop methods that will allow us to extract the indicators from multiple different layers in the stack. We'll have built a background mapping of those indicators to the properties that are key to characterizing the software styles. We'll pull everything into a common data representation, and then we'll use those formalized definitions that we've developed for communication styles to now predict multiple styles from a single code graph. And so if we think back to the core of the project, our ultimate goal is to be able not just to detect a nonconformance in one particular software style, but to arbitrarily detect nonconformances across many styles and across many families. So our intent here is to do a small amount of manual extraction to identify those enduring indicators that allow us to characterize these properties such that we can build a set of predictors that will allow us to actually characterize multiple types of styles and in a much more enduring way. So thinking about where we are with this project, we've done a lot of great work. In this year, we've managed to build the prototype predictor that uses a rules-based approach to extract publishers and subscribers that are built on a framework. We were able to demonstrate that we could use that same approach for multiple different frameworks, which gives us confidence that the work that we're doing right now will take us to where we'd like to go in the future. So right now we've done this formalization of defining communication styles. We're currently extracting those indicators of properties that characterize those communication styles from multiple layers across the software stack. We'll integrate these additional sources of information into a single feature space, which will allow us to achieve more generalizability within the family of communication styles. And where we'd like to go is to extend the work that we did for communication styles to other software style families, identify what additional properties may be necessary to characterize styles in these other families, and build machine learning-based predictors that are able to predict multiple styles in a single predictor, or if that's not possible, to build multiple machine learning-based predictors that would detect all of these different styles. We're excited to identify really good case study examples from open source and from potential collaboration partners as we extend this work. For a case where we have a narrow case and a pretty well-characterized nonconformance, we can already use the technology that we built for publish subscribe and the rules-based approach. As we move forward, we're looking for projects that have multiple types of communication realized in a single project to demonstrate that we can separately characterize multiple different styles from a single project and a single representation. With that, I'd like to thank the team and thank you, and open it up to questions.